in Korea. He then went on to get his PhD at Iowa State University, and he spent some time as a postdoc at UC Riverside. And in 2006, he joined the faculty at West Virginia, and that's where he's been ever since. Today, he's going to talk to us about the detection and management. Oh, I forgot to mention, he's also president of the Eastern branch of ESA, in case you didn't know. His title of his seminar is Detection and Management of Invasive Pests Using Drones and Artificial Intelligence. And with that, I will turn it over to you.
Okay. Hey, thanks, George, for the introduction. Hey, I'm very glad to meet you all. I'm from West Virginia here. Okay, so, okay, keep in mind, I'm an entomologist. I'm not an engineer, okay? So let's start with this video. So can you find insects? This is actually drone footage on the bean plot here on the university, West Virginia University. Yeah, try to see if you can see or spot insects. So my point here is, we believe that if insects are so small to be detected by drones or satellite, right? So I'm going to change that kind of your mind a little bit today with modern technologies that can be applied to entomology. So we'll revisit this again. So how many insects did you find? Okay, so let's go. So I'm in West Virginia. So West Virginia is a little bit bigger than New Jersey. And then eastern part of West Virginia is kind of mountain. And the western part is kind of plain. So we have a major commodity is forest, like timbers. But we have animals here in West Virginia. So we have a lot of field crops and forage crops. And the eastern panhandle record here near Maryland. So we have apple production, apple and peach production there. So that's kind of West Virginia. One of the problem we have is we don't have a lot of entomologists in the state. So there is no way for entomologists to cover our 55 counties in West Virginia. So that's why we need some technology. It can cover a large area with limited resources, especially human resources. So that's what I'm going to talk about it. So West Virginia University is on the top of West Virginia. It's very close to Pennsylvania. Okay, so today's topic is related to precision agriculture in a big picture. And also we call it smart forestry. So that's kind of the area of talk for today. So I have some expectation from this seminar for you. So if you're an expert in this kind of system, you may learn about some current development of using drones and AIs for pest management. If you're a beginner, this may be a good introduction of using drones and AI for pest management. If you're a non-user, that's totally fine. You may get some ideas of using drones for your research or pest management. So it can be applied to urban system, right? And it can be applied to agricultural system, forest system. Yeah, let's say detecting a mosquito. It seems impossible, but it may be possible if you listen to this seminar today. So that's the expectation. So let's start with the drone. So we need to define the drone. So actually, the official term used by the Federal Aviation Administration, FAA, is SUAS, Small Unmanned Aircraft System. So that's the official term. But sometimes we use a UAV or UAS. Long time ago, we used the RCA, remotely controlled aircraft. But today's talk, I just use a drone, but official term is SUAS. Okay. We have two types of drones. One is a rotary wing, and the other is a fixed wing. So fixed wing is just like airplane. Right? The rotary wing is like helicopter. So the good thing for rotary wing drone is it can stay in the air. We call the hovering. So it can hover in the air so that it can take a good still picture. But it cannot fly very fast or long distance. Fixed wing drone, it can fly long distance and very fast. So depending on mission, you can pick to choose this platform. Okay, so drone is just a vehicle, just airplane. But depending on what sensor you put and what other system you put into the drone, and that defines the function. Okay, so if you put the natural color cameras, just normal cameras, it'll take a picture. If you put the thermal camera, like in the second one, and you may be able to find, animals escaped from the farm, or if you use a spectral sensor, you may see the a feeding damage of insects or disease, that kind of thing. So depending on what sensor you put on the drone, it defines the function of the drone. Okay. So the drone we are going to talk about today is autonomous drone. So actually, we don't fly drone because we program it and then we push the button. It can be done because it is a satellite guided with GPS, and then we command, go there, take a picture, go there, spray pesticide, we come back, and it'll do it. Again, we generally don't fly drone. We still fly with the autopilot. So keep in mind. So this is the first drone I used in 2008. Whoa, this is about 15 years ago. So this was the first drone. It's a fixed wing drone. It is about 5 feet by 6 feet. It's pretty big. It can fly 60 miles per hour. So again, this is fixed wing drone. This is a styrofoam based, which means very light. You can actually pick it up. And then we put the camera on the bottom so that when it flies, it can take pictures. We call the aerial photography, right? So, and that become the data we are going to use. Okay, so this is the first aerial shot from that drone in 2008 or 9, that area. So this is in the middle of nowhere. We have a lot of places like that in the middle of nowhere in West Virginia. We took picture and we see the car. We see a car. We zoomed in, and then we know the width of this lane is about 3 meters. And if you're a car expert, you may be able to identify this car. And even, can you see small registration tags on the windshield? So this is a 2" by 3" in West Virginia. And we change color every year. So green color means 2008. So we get a lot of information with just based on this one shot from the fast flying drone. Very encouraging. This means anything bigger than 2" by 3", we may be able to detect it, right? So that's the idea. So my lab's drone project started about 2008 again, and then we tried to detect something not moving. So how about invasive plant, right? They are not moving like insects. Okay, and then we tried to detect insects. And then we used a sensor later, about 10 years ago. And then we tried to not only just detecting, we tried to deliver control measures such as pesticide and natural enemies. So I'm going to talk about natural enemy release by the drone today. And then during the past 2 to 3 years, we have been working on artificial intelligence, machine learning. So that we don't have to look at the image even, the machine, again, program automatically detect from the images obtained by the drone. So that's the kind of talk I'm going to go through it. So the first thing first, 2009, we went to California. So California, Central Valley, from West Virginia is far away, right? So California vineyard is good because it is I was a postdoc there. That's the first reason. And second, the size of actually the area is about 15 mile by 15 mile of vineyard. And detecting pests is pretty hard. So one of the problems the grower we worked with had was morning glory. Morning glory is a vine, so it prohibits growers from harvesting or picking the grape because of the vine. So growers want to know where the morning glories are so that they can go and whack it. So at that time, there was flowers, morning glory flowers. So why don't we detect morning glory flowers? And then let growers know so that he can go and remove it. before harvest. So that's the idea. So we form a team from West Virginia and California. And then we did the field coordination. Again, we don't fly. We program it and then make the drone fly in serpentine pattern like this so that it can cover entire vineyard. Okay, and then because the camera is going to continuously taking aerial photos, and then when we download it, it looks like this, and then we have to stitch it together. We generally use 70 or 80% overlap of each image so that there is a common area so that we can stitch it. But again, 14 years ago, we didn't have a lot of good programs doing this. But these days, we have so many good programs, so you don't have to worry about this part anymore. So we flew. Again, we programmed. And then the drone carries a GPS and 10 megapixel camera. I know this is nothing, right? Your cell phone may have a 20 megapixel camera, but at that time, 14 years ago, this was the top brand and top resolution you can get. We paid about $3,000 for this camera. Okay, and then this is one of the example shot. So this is actually vineyard, the edge of the vineyard. Can you see morning glory? No? Okay. So how about this way? We enhance the image. And then if you see small red box here, you may see a little bit of morning glory flower, right? And then we put the opposite, we call the filter, right? Opposite color. So purple versus cyan, and then it shows up. So what we did was, for example, A is the original image. B is enhanced image. C, we put the filter, and D, we give a command, make it black and white. So all of these white things become flower. Black is the background. Everything was done in Photoshop at the time, because again, 14 years ago, we didn't have a lot of good programs for that. So this is one of the results. So all of these white dots are morning glory flowers. So, and we can get the geo coordinate of each morning glory flowers. So we were very happy with this. And the reason is that if we can detect morning glory flowers, anything bigger than morning glory flowers, we can detect it. So we have a lot of insect damage or insect signs or disease symptoms. It's bigger than morning glory flowers. So it opens up a lot of opportunities for us to do further study. So excited. But you have to know that drone crashes. So we had one crash during the mission in California. So it happens, right? But my engineering partner is still happy. You know why? Because we put this actually drone together with the glue, and we flew again. Again, this is styrofoam-based drone, so we can put together with the glue again. So that was the first thing we did. And then, okay, can we detect insects? Challenging ourselves. So what we did was we made a 1 meter by 1 meter small plant bed, and we planted, we planted a cowpea in this case. And we put some insect specimens there. We hid them to see if drone image can pick it up. And then we flew the same drone again. And this is the one of the shot. And you can see up there, that's a globe. Can you see the size? And this is 1 meter by 1 meter plant bed. This is about 15 meters or 45 feet above the ground. And now we can zoom in, right? So if you zoom in, we see 6 butterflies, which are listed here. And most of entomologists were able to identify it even with this image. And other small insects hidden in this plant bed, we couldn't see it. Because again, this is a 10 megapixel image taken from 15 meter or 45 feet above the ground. But the good thing is anything, again, going back to the resolution, anything bigger than 3 inches, we may be able to see. Okay. So even in cowpea, you can see some feeding damage here because we had some feed damaged cowpea. So it's a good thing. So what we learned was using fixed wing airplane, fixed wing drone is very hard because it flies so fast and it cannot hover or stay in the air. So we changed our platform from fixed wing to rotor wing so that we can get a high resolution and still picture, still photograph. So what we start with the drone in a bucket, that's our project name. And then we have a small rotor wing drone, and then we put the Canon HECT camera. So this is a small point shoot camera, but we put the spyware into the camera and then we control it so that we can say every 3 seconds take a picture and then it'll take a picture every 3 seconds, or zoom in and then take a picture and then it'll zoom in and take a picture without manipulating using our hands. So that was good. So he was our pilot at the time. And then the first mission we had was detecting eastern tent caterpillar. West Virginia have quite a big problem in early spring. So this is actually tent made by tent caterpillar. So can we detect or can we count number of eastern tent caterpillar tent? And then this was the first shot. Resolution is not good, but still we can count all of these eastern tent caterpillar tents. And the amazing thing is we did the ground counting too, but we found twice more tent from the aerial image than ground. So it was exciting. And then recently, about 5 years ago, I was actually I did my sabbatical in South Korea, and this actually this work is done during my sabbatical leave. So in South Korea, there's a urban problem with this slug moth because they actually defoliate poplar trees. Okay, so and then they have so this is a slug moth and this is a pupa. So pupa cap is open, which means the adults came out. So this one doesn't have the moth anymore. So one of the problems they have was there is the economic injury level, which means about 5 or 6 cocoons per branch or tree. And then what they do is early in the spring, when they hatch, they lay eggs and hatch, and then they apply pesticide. The pesticide application is based on number of cocoons on the poplar trees. So if you see this ground view, I can count 1, 2, 3, 4, 5, 5 cocoons. So one of the problem is, if you see from the ground, you don't see this kind of open cap. And this should not be counted as a cocoon because nothing is inside. So that's why we did this study and how much actually error we have. So this is an aerial view. And then if you see this one, 1, 2, 3, 4, 5, 6, there are 6 cocoons, but 5 of them are already empty. So actually there are only 1 live cocoon here. If you do only from the ground survey, the decision is apply pesticide. But based on area survey, this is not apply pesticide. That should be the decision. So we counted number of fixers, accounting for this exit holes. So that's the study. And this was published in a couple of years ago. So if you want to look at it, so this Journal of Economic Entomology, I think you can find it. So x-axis is the actual number of cocoons, and the y-axis is by the survey. If you use ground and visual survey, there is a way more overestimation. Y=X is the actual number of cocoon, right? So it's overestimating. Drone is underestimating a little bit, but still their regression line is very tight, which means we can say, a certain percent of cocoons can be found by, drone. So that was the conclusion. So now what I'm trying to say is we can detect insects using drone, maybe non-moving stage. Okay, so we talked everything. We talked about natural color camera so far, but as time goes, we see some limitation of using visual or RGB, we call the RGB sensors, normal camera. So we started using the sensors. So something human eye cannot detect it, but actually the sensor can detect it. So the first one was a thermal sensors. Thermal sensors means it record the temperature of the object. So if you look at A, so B is on the flower, and then if you see the thermal camera, you cannot see the bees much because insects are cold-blooded, right? So I cannot cold-blooded, but so their body temperature is similar to ambient temperature. Surely we should not be able to see it. But when they fly, they use the flight muscle, which is on the thorax, and the temperature goes up to human temperature sometimes. So now we can detect it. So now can you see that C is the normal camera and D is thermal camera. So E is normal camera. I don't know, can you see bumblebee? Okay, if you know, it's right here, but it's hard to see sometimes. But thermal camera will show you exactly where it is. And also there is a technology called MSX, so you can put two images together. So this technology was already available 8 years ago. So now we are using it for insect detection. I'll show you interesting video. So we do the bee study, and I'm gonna show you. So this is actually a Japanese homepage bee. That's a thermal camera. If you see, there is actually the fireball is moving. That's the bee, because flying bee use a flight muscle, and then temperature goes up to 31 degrees Celsius, which is higher than normal temperature. That's why you can see the bee movement. So we had the project making a pollination robot with engineers, and we tried to see bee behaviors, but it's hard to see them. So we use the thermal camera to chase them, how they come and go from the nest, that kind of things. So, okay, what about detecting insect signs, such as for webworm, which means they make a web. This in the fall. In the spring, it's a tent caterpillar. In the fall, different species called fort webworm, and they make a web. We have a lot of problem in West Virginia again. We have so many trees. So this is the thermal imaging. So if you see in the middle of the web is 6 degrees Celsius higher than the lowest temperature or surrounding. So which means we can detect this fort webworm web easily. So the question is, can you put this camera in the drone so that we can fly over forest and finding all of this fort webworm? Yes, we do. That's what we are doing these days. Okay, so now, okay, let me go back. So I showed you bean plot, right? And I don't know how many of you saw the insects, but at the same time, we put the thermal camera, which means there is a thermal images, videos. So I'm gonna show you, and then you will see. So on the top, this one is what you saw in the early this presentation, and this is the same thing, but it's with the thermal camera. So if you see, it's a flying insect should be shown on the thermal camera because they're, can you see that here? Yeah, I saw one. Okay, here's another one. Okay, here we go. There's another one, 3, 4, 5, 6. So because, with the normal camera, you may not be able to see it. But with the thermal camera, you can find flying insects. If insects are under leaves resting, you may not be able to see it because their body temperature is the same as ambient temperature. So, okay. Okay, so that's the kind of the insect detection. So we are keep moving to further and further with drones and sensors. Now, actually, we are detecting invasive insects and disease. So we are talking about gypsy moth. So right now, it's called a sponge moth. That's the right term. So we also use a satellite to detect the sponge moth because the damage is so extent in multiple states. So what you see here in the like a brown spot, those actually the defoliated area. But we want to make sure that it's done by gypsy moth or sponge moths. So we fly drone, okay, and then fly detail. So this is in June, and it looks like it's totally defoliated. And then we do ground survey to confirm it. And then this database can be used for machine learning. So that's the kind of idea. So this is actually the Pennsylvania Allegheny National Forest. Again, it's a June. And you see all of this 100% defoliation by sponge moth. And some of these trees are intact. So geneticists may be interested in all of these surviving trees, right? And then we also found that, can you see, there is actually defoliation, linear defoliation. We were so wondered how gypsy moth can make this kind of linear defoliation about 2 to 3 miles in length. So we went there and flew over, and this is a linear defoliation by gypsy moth. This is about 2 to 3 miles. Wow, how can they do that? And then later we found that they put the BTK, which is microbial the pesticide, with the helicopter, but there was a drift. So when they fly, the BTK was drift to the one side. So that's why that area was not, treated with the BTK. So that's why you can see this kind of linear damage. And right thing is thermal. Okay, so thermal means when actually insects, the trees are defoliated by insects, we can see more the ground soil, so which means it become hotter. So that's another way we can see. So what we do so far, and these are the list of insects and disease and weed we have been detecting using drones and sensors. There are quite a bit. So we have a tree of heaven here. So we do tree of heaven detection because we want to detect spotted lanternfly. Okay. So if you're interested in any of these invasives, let me know. We'll help you. Okay. So we used a drone, and now we detect invasive plants or invasive species using sensors. Is that it? And then now actually we try to deliver or release natural enemies using drones. So our target invasive plant is Myrominid, Perscaria foliata. So this is from Asia. I think New Jersey has a big problem too. So triangular leaves. This is actually the key characteristic, and this is a vine, and it has a thorn on the leaf, on the stem, so it is very hard to remove physically. And then this is a bird dispersed, and by the seed, the bird dispersed plants, and birds eat the seeds, and then they poop, and then that's the place where new Myrominid population starts. So in West Virginia, they actually overtop small trees and kill the trees, believe it or not. So that's why we need to control this weed. Again, it is very hard to do manual or physical or mechanical control is very difficult. And then sometimes it occurs in the middle of nowhere where human cannot access. That's the problem. So the good news is that we have a herbivore, we call it predator. So we have an herbivore, so which is a weaver. It's called a Myrominid weaver. It's so tiny, but they are eating. So we try to release this natural enemy insects to the Myrominid patches detected by the drones and sensors. So right now it's $1 per bug. And the New Jersey has a beneficial insect lab at New Jersey Department of Ag, and they produce it. It's pretty expensive. Because it's expensive and then numbers are limited, so current release method is you have to bring this insects and to the weed patch in the field and then hand release it. This is good, but the problem is we are not controlling anything in the middle of nowhere because number one, we cannot detect it. Number two, it is hard to access. right? So that's the problem. So what we tried to do was we use again autonomous drones. We program it and then find the weaver, find the weed and drop the weaver, and find another weed patch and drop the weaver and return back. So that's our autonomous flight. Okay, the first thing first, we have to detect it first, right? So we did a series of study. What altitude, what sensors we need to use to detect miter minute weed, and then we found that less than 25 meters above the ground using RGB camera is enough to detect miter minute without going and checking. So this is about 35 acre field. It's very steep terrain and nobody can go there. But drone can do it because it fly over this steep terrain. And then these actually red areas are the weed patches. So miter minute weed patches. What's next? We cannot go there and then mechanically remove it because it's a steep terrain. It's very dangerous. So what we are going to do is we are going to drop our weaver in each of these weed patch. Okay, so idea is, so we have a miter minute weaver, and then we put into we call the bug pod, and bug pod is loaded to the drone. Oh man. And then this drone goes to the field, find the miter minute, and then drop it. And then insect comes out of the bug pod. So that's the idea. We have 3 generations of bug pod. Originally, we called the bug bomb, and the journal didn't like it because it's bomb, so we changed the bug pod. So anyway, so this is a first generation bug pod. Simple, it's like a paper carton, and then put the straw, cut straw, and then clog with the clay. Okay, and then back, you put the insects, weaver, and then you put the cotton. And then it drops. The idea is it drops and then, cap opens and insect come out. So this is our bug pod test. My engineering partner is grabbing bug pod and then dropping because at that time, dropping from drone was illegal. Okay, so we have to follow the FAA regulation again. So dropping pod is illegal at the time. So we have to do hand dropping. So when it comes down, like if clay is broken, and can you see miter minute weavers? Those are the weavers. So that's the test. Okay, so now actually we have to have something to drop these bombs or pod, right? So we have to make a dispenser. So dispenser is very simple. There's one hole on the bottom, and then this is actually revolving, turning. And when this turn, this one is go there and then drop it. Okay, so this is called the dispenser. Okay, put the dispenser on the drone, underneath drone, right? And then you go up and then drop one by one. So we have, this is an actual field test. So we have lots of bug pod or bug bombs, and then we are loading weavers into the bug bomb or bug pod. And then we did an area survey, and these are the places where a miter minute was found based on area image analysis. It was 2014. Wow, it's 9 years ago. Oof. And then we were advanced a little bit, so we had a field monitor, and then we are watching monitor, and then where the drones are, where the miter minute weeds are, and that kind of things. So this was our prototype, and there's a drone, like a rotary drone, and then we have a dispenser. And then it drops, it lands, surely cap is open. But what we have to do is we have to go very fast to actually retrieve it, so that we make sure insects are okay and everything, right? So we checked all the legs are there, all the antenna there. That's the first thing we checked. Second, we tested for walking. We have to make sure they mate after dropping. and then they have to feed, right? So we did all of these tests. And then we found there's no negative effect on weavers by area release. So survivorship, there was no differences with the control compared to control, and feeding amount was no difference. Actually, we found that the weavers did the air travel fed more after they returned back to the ground, but no significant differences. So we published this one in 2008. We couldn't publish earlier because it was illegal. Again, dropping thing from the drone was illegal. So we had to have special permit to do that. And then, so we published 2008, and this was the first paper in the world dropping natural enemies using drones. And then now actually a lot of people use it. And there's one company in California there. So and it's good. So this is second generation bug pod, or we call it bug bar. Because making bug pod was very difficult and tedious. And second, growers didn't like it because there is a straw plastic. So growers don't want to have a plastic on their field, on their farm. So we had to change our bug bomb. So this is what we call the bug bar. And we put insects inside bug bar, right? And the same way. And this is the weaver, and this is the actual bug bar. We made this one from 3D printing. So we don't actually make it. We print it using polyvinyl alcohol, PVA. This is a biodegradable material. So once you release it, this is actually the material reserved. No harm for environment. Okay. And then putting insect inside is hard. Into the board is hard. So we made a special. This is not special. This is a vacuum basically. You know, it's a vacuum, but you can actually suck the insects into the board easily. So if you want to see this development, second generation of bug board, we published in Journal of Economic Entomology 2 years ago. So the last one I want to talk is AI and machine learning for pest detection. So what we learned so far was whenever we fly, we get about 2 terabytes of images per day. That's a lot. 2 terabytes image, those are a lot. So we learned that we cannot do manually. So we need some automation. And that's where AI and machine learning kicked in. So biological invasion curve. So when invasive species arrive and then before establishment, that's the time we can eradicate. So what Forest Service, specifically for Forest Service, is doing is early detection and rapid response. It's called the EDRR. So if EDRR is success, you know, we don't have to about the spread and management. But if we fail EDRR, then now we have to manage and restore. So that's the idea. So early detection of invasive pests, that was the goal for the next thing. So right now, actually, the Forest Service folks and state folks in the Forest Service or Forestry Department is doing ground survey, but they don't just do ground survey. They use satellite image to guide it or area sketch mapping to guide it. Okay, area sketch mapping means the people like a ride in an airplane or a helicopter and then look through the window, and if they see the damage and they actually sketch it on their like a sketch pad, which has or kind of similar to GIS. If you like draw it, it shows location and you know the areas. So they use this kind of technology. So that's what we call the traditional EDR, early detection and rapid response. So, but the problem is satellite and the area sketch mapping doesn't have a good resolution. So what we have been developing is we call the drone and AI empowered EDRR. So basically we download a satellite image, we put into the machine learning, and then machine will tell us where to fly drone. And then we fly drone and put the image to the machine learning. And then machine will say where to do ground survey. And then we do the ground survey and put the data and go back to the machine learning. So the more we do this, the machine getting smarter and smarter. And that's the idea. And then later we may be able to use it. So machine learning, just quick definition of machine learning. So you need to compare with the algorithmic solutions. So for example, you have a computer, right? And you install a program, let's say Photoshop, ImageJ, right? And then you put the data, and then you put the function, and then you get the output. So that's actually the normal program, software, and apps in your computer or even cell phone. Machine learning is a little bit different. You have a computer where we put the data, but not just data, a lot of data. And then we don't put the program, we put the output. We put the output, a lot of output, and then computer makes a program. So this program can be used for our purpose. So program versus software versus machine learning, the biggest difference is what's the output. Computer will say what you need, but machine learning will generate program that you need. So that's actually machine learning. So we used machine learning for ash decline detection caused by emerald ash borer. So this is invasive pest, and they damage under the bark and eat the cambium, so that it blocks the nutrition movement, and then eventually it killed the ash trees. Big problem. So to detect this, we collected more than 6,000 images. 6,000 images, and then we have to annotate it, which means we have to say which one is ash decline. So when we talk about machine learning, yeah, it's cool, but there are a lot of labor behind, because somebody has to do at least one time saying what that is. So this is actually ash damage by the emerald ash borer. If you see from the ground, the bee, it looks like a brown dead branches. But if you see from the sky, it's always white. So dead trees looks white from the aerial image. And then also it has we call the opposite branching pattern. So that's the key to identify the ash trees. So all of these dying ash trees showing this kind of opposite branching pattern. So those are the key to train our machine. So we use the deep learning. Okay, so you know ChatGPT. So GPT means generative, pre-trained, transformer, right? So generative means they generate. Pre-trained means they used a lot of data, train it. And transformer, that's actually the model of machine learning, what they used. So we use the deep learning with it's called mask to former. That's the model. So mask to former, what they do is they separate all the features on the image, and then they analyze it. Okay, so they separate this part, and they separate this the lake part, and then they analyze separately, and then they put it together. So we use the training data, validating data, and testing data, and then we trained this machine, and this is what we've got. So this is input image, and this is predicted by deep learning, mask to former model, and then this is ground truth data. Really good, but not always. So this was the input data. We have a car here, and then somehow our deep learning model says car is ash tree, and then this is ground data. So right now, actually, it's not perfect, but the thing is, we never trained car to our machine. So we can train car, then it is separated. The more data we put, again, the machine is smarter and smarter. That's the idea. So what we really get is actually, this is one of the aerial image of ash tree on this really steep area, like even cliff, and this is the lake. Nobody can go there and then determine this is an ash tree or not, but drone can do it now. And then when we put this image into our deep learning model, what it shows up is not yes or no. They will give us probability. So in this box, let's say in this box, purple box, there is a 98% there are declining ash trees. In small box, there are 97% of chance that we have declining estuaries. So what they spit out is not yes or no, it'll spit out the probability so that we can actually use it. It's more useful. So we did the actual big validation study. It's about like 40 hectares, so about more than 100 acre, I guess, areas in West Virginia and Pennsylvania. So we have about 9 sites. And we don't fly drone. We did an autopilot, and then we download image, and we have to stitch it, and then we put into the georeferenced map. Using the map, this map will go through the deep learning algorithm, and then they will show us where the declining estuary is. So this is one of the example. So when you see red, this is actually what deep learning says there are estuaries dying. The white boxes, those are ground survey determined. So hit and miss, but machine did a really good job. And when we talk about type 1 and type 2 errors, false positive and false negative, it's about 5%. This is a really good result. And then again, the more we put the data, machine will be smarter and more accurate. So that's the kind of idea. So I'm finishing up actually. So right now, actually, we have the way it works as of today is we have operation and data analysis and interpretation. That's the key part when we use drones and sensors and AIs for pest detection and management. Operation part, we have a pilot and drone. These are well established, so we don't have a problem with the operation. Even you don't have to fly again, we program it. Even data analysis, we have an analyst, more likely image analyst or engineer developing deep learning or image detection. We have a software out there, not a big problem. The biggest problem is expert who are going to interpret. This is where entomologists should be. So we have autopilot and we have auto detection, but we don't have a new workforce. And I don't think any of our entomology department in the United States, even in the world, is teaching these things. But again, this is where we are going. And I'm 100% sure there will be more job markets for this. Okay, so we are right here. We are focusing on, not we, I mean, the industry is focusing in data analysis and making deep learning. But again, next step, I guess Rutgers, West Virginia University, we should generate new workforce for this kind of things. I have a lot of collaborator in Forest Service. And also I have a lot of entomology and engineering colleagues in California, West Virginia University. Even we fly drone in winter and we have to start because it's so cold. They're so fun. And fortunately, I had a lot of funding agencies to develop this kind of projects so far. And then also we have been surveying tree of heaven with the sensors and to detect actually spotted lanternfly, but spotted lanternfly flew into our drone and it looks like they love some heats. Okay, that's what I have today and I take any questions.
Well, thank you very much. That was excellent. Very interesting. Do we have any questions? I think Juan has his hand up. Go ahead.